Speaker of this morning session is Rosengarten. He speaks on the rational point of linear algebraic groups.
Thank you. So it's a pleasure to speak at this conference in honor of Jacques Tietz, whose work, I never met him, but his work inspired a lot of my own. So I'm happy to be here. So I'm going to start out by introducing, it's rational points on linear algebraic groups, and I'm going to start out by introducing some of the objects that will play an important role in the talk. So many of you may be familiar with them, but for those who are rusty or haven't seen them, let me just begin with these. So UN, this is the group of upper triangular unipotent matrices. So these are n by n matrices that have ones along diagonal, zeros below, and whatever you want above. Okay, and a unipotent group is just a Zariski closed subgroup of some UN. Okay, so that'll be my definition. That's, in fact, the definition of a unipotent group. Okay. So an example, an important example, is the group U2. So this is matrices of the form 1, anything, 0, 1. If you multiply two of these matrices, you're just adding this entry. Okay, so this is none other. Sorry. Can you see everything above here? Let me do this. Okay, so example is U2, which is the set of matrices of the form 1, anything, 0, 1. So if you multiply two of these, you're just adding this entry. So this is none other than the additive group GA. Okay? Now, if you're working over a field K of characteristic 0, then every unipotent group admits a filtration, like so, where each of the successive quotients is isomorphic to the additive group. Okay? Now, if K has characteristic P, this isn't true anymore. So for one thing, unipotent groups in characteristic P don't have to be smooth or connected. But I'm mainly going to be interested in the smooth connected case. So let me concentrate on that. Even then, something can go wrong. So if K is perfect, then things are good. Then every unipotent group over K is split, which just means there exists filtration as above. So there's a filtration with quotients all isomorphic to GA. So a filtration like this. Okay? But if K is imperfect, this is completely false. So here's an example. So K is imperfect, so you can choose an element A in K that's not a pth power. And we can take the group U, which is defined by the following equation, y to the p, let me write it this way, minus ax to the p minus x equals 0. This is a subgroup of GA times GA. Okay? It's unipotent because it's a subgroup of this unipotent group. And U, so U is one-dimensional. But I claim, and in fact, actually, it's not hard to check that if you extend scalars to this purely inseparable extension, this becomes isomorphic to GA. Okay, so it's in particular, it's smooth and connected. But U doesn't contain a copy of GA, so it can't have this filtration. If it contained such a copy, it would have to be an isomorphism for dimension reasons. U is not isomorphic to GA. So this is not hard to see. What you do is, if you're isomorphic to GA, then in particular as a scheme, as a K-scheme, you're just the affine line. And that would mean that there's in particular a non-constant map, let's say F, from A1 to U. And what is a non-constant map from the affine line to U? It's just a pair of polynomials that satisfy this equation. Okay? So y of t to the p minus a x of t to the p minus x of t is 0 with xy non-constant. Okay? Now, if you have this, then looking at leading terms, right? So if, let's say, x, y are the leading terms of big X and big Y respectively, then just by comparing leading terms on both sides, you get that y to the p minus ax to the p is 0. Okay, and then you just, this implies that x equals y equals 0. Because if x is not 0, you can solve for a and get that it's a pth power. So x is 0, and therefore y is 0. Okay, and then this is a contradiction, because these were supposed to be non-constant polynomials. One of them has non-zero leading term. Okay. So U is not isomorphic to GA, and in particular doesn't contain a copy of GA, at least over K. So such groups, they were introduced by Tietz. So a smooth, connected, unipotent K group, U, is called wound when it doesn't contain a copy of the additive group. Okay, so if I have a general smooth connected unipotent group over K, so U is, let's say, smooth connected unipotent, so if U contains a copy of the additive group, then it's not hard to show it contains a normal copy, and in fact even a central copy. And so what you can do is you can sort of keep pulling out all the GAs and quotienting by them repeatedly until you wind up with a quotient. So you have this sort of filtration. This quotient, so where this is split, submits a filtration by GAs, and this is wound. Okay, so you can always throw out all the split stuff and you wind up with something wound. All right? Okay, now these wound groups play a central role in the theory of linear algebraic groups over imperfect fields for a variety of reasons. Because of time constraints, I'll just give one that's relevant to what I'm talking about today. Okay, so groups play a central role in the theory of linear algebraic groups over imperfect fields. Okay, so let me mention, for instance, the open cell decomposition. Okay, so let G be a, it doesn't actually have to be, but let's say smooth connected linear algebraic K group. Okay, and let, okay, I'll do it this way. Let's say T inside G is a split torus. If one chooses a sufficiently general co-character of this torus, lambda, then associated to it one has a so-called open cell decomposition where you have an open immersion like this, where, okay, what are all these things? So U plus, U minus are split unipotent K subgroups of G. Okay, and ZG of T is just the centralizer of T inside G. Centralizer of this torus. And this is the multiplication map. And the point is that this is an open immersion. So this means that for the purposes of many questions, in particular, let's say questions related that are sort of invariant under birationality. So this is your G, it's birational to this open subscheme. For such questions, it suffices to understand this thing. And U plus and U minus are very simple. Think of them as sort of being easy. They're split unipotent, and every split unipotent group is, as a variety, just an affine space. Okay, so just AN for some N. So these are sort of simple, and this is the sort of more mysterious object, the centralizer of T. If T is maximal, now, of course, there's an issue here. You may object. G may not contain a split maximal torus. I'm going to think of that as being not a big deal somehow, because from my perspective, the difficulty arises from all the phenomena for imperfect fields and things that relate to separable extensions, like, for instance, splitting this torus, I'm going to regard as being easy for my purposes. And that, in practice, that's often true. When you don't have the crutch of Galois theory over imperfect fields, the situation is much more complicated. So Galois stuff, I don't worry about. So the fact that this thing isn't split over K, but maybe over a finite Galois extension, I'll regard as not that significant. Okay, but let's suppose that I have my split maximal torus T. Then I can consider this quotient, Zg of T mod T. Because of the maximality of T, this thing has there's no room left for any torus here, so this has no torus. This is unipotent. In fact, I should say it's smooth connected unipotent. Okay? And then again, if I have a smooth connected unipotent group, I have this filtration, and this part is sort of easy, and it's the wound quotient that's subtle. Okay, so for the purposes of many questions, because of, for instance, this open cell decomposition, and for other reasons too, often you're reduced to studying wound unipotent groups. Okay? All right. So it depends what you want to do, right? This is why I'm being sort of vague here. So actually, my main interest today will be in questions related to density of rational points and unirationality. And those are both birational questions. So the variety structure is all that matters. Yeah. Okay. So now that I'm past sort of the introductory remarks, let me mention the sort of theorem of Oesterlé's that sort of started most of the stuff I'm talking about in this talk. So it's 1984. It's from his paper on Tamagawa numbers and unipotent groups. So if U is a wound unipotent group over K, which is a global function field. Okay, so you should think, so it's the function field of a curve over a finite field. So you could think, for instance, FQ adjoint T. Okay. Function field of P1 over FQ. So U is a wound unipotent group over a global function field, and the dimension of U is strictly less than P minus 1. P is the characteristic always. Then U has only finitely many rational points. Okay. So this is Oesterlé's theorem. He proved it by some playing around with equations. Now there's a natural question here, which is, do you need this assumption, and is it optimal? Okay, so you do need it, and it is optimal. So here's an example. Take U. Okay, so first of all, consider the group. So I have restrict scalars from K to the 1 over P down to K. Group GM. Okay, so what is the dimension of this thing, first of all? So for any function field, so if you look at like FQ joint T, K to the 1 over P is just FQ adjoint T to the 1 over P. Okay, so K to the 1 over P is a degree P extension of K. So this is a degree P extension, this is one-dimensional, so this is P-dimensional. Okay. Now inside of here, I have a natural copy of GM. This corresponds to the inclusion of K cross inside of K to the 1 over P cross. Okay? And so what I can do is I can take U to be the quotient. Let me leave that. So take U to be the quotient. The Weber restriction of GM modulo this copy of GM sitting inside. And now this is P minus 1 dimensional. It's smooth and connected because this thing is smooth and connected. I claim it's wound unipotent. So to see that it's unipotent, for instance, if you look at the level of rational points, if you take something in this numerator, you take something K to the 1 over P cross and you multiply by P, which is to say raise it to the Pth power, you land inside K cross, which is the bottom. Okay, so using similar reasoning, you can conclude that this thing is a P torsion group. And a smooth connected P torsion group is necessarily unipotent. Okay, so this is unipotent. To show it's wound is not very difficult. Basically, the idea is that you need to show that there's no non-constant map from the affine line to this thing, this numerator. You need to do a little more, but let me not worry about it. Okay, and such a map, by the definition of a restriction, is the same thing as a map of k to the 1 over p schemes from here to gm, which is to say a global unit of the affine line over this field. And the only units on the affine line over a field are just the constants. So this is a constant map, and therefore this is a constant map. Okay? So this is actually wound unipotent. Yeah, so that was the thing I didn't say. That's right, yeah. That was the little more I was referring to. Yeah. Right. So this is a unipotent group wound of dimension p minus 1, but I claim it has lots of rational points. The reason this has lots of rational points is if you take the numerator, so Gm is an open subvariety of the affine line. So this is an open subvariety of the Weil restriction of the affine line. And this is non-canonically, so if you choose a basis for this field over this one, you'd get an isomorphism between this Weil restriction and the affine line over k, dimension p. P is the dimension of this extension, the degree of this extension. So this is an open subvariety of an affine space, and therefore, so it's rational, so it has lots of rational points. And therefore, this quotient u is unirational. It has a dominant map, in fact, a surjective map from a rational variety. And therefore, u of k is, not only is it infinite, but u of k is actually Zariski dense in U. Okay? Okay, so this dimension bound is sharp. You can't relax it to equality even. Now, of course, there's a natural question which Oesterle asked, which is if you have lots of rational, so in some sense, his question is this dimension bound sort of a red herring, and the real point is not the dimension, but these unirational subgroups. Okay? So his question is, if u of k is infinite, again, so k is a global function field here, u of k is infinite, must u contain a non-trivial unirational k subgroup. Okay. So first of all, he phrased this question when U is wound unipotent, but you can, of course, relax it to any connected linear algebraic group, or even not connected, any linear algebraic group. Let me also slightly, seemingly strengthen the question, although they're non-trivially equivalent, but so let me ask a slightly strengthened question. If G is a linear algebraic group over K, global function field, with G of K Zariski dense in G, must G be unirational. Okay? So this, an affirmative answer to this implies an affirmative answer to this by just replacing U with the identity component of the Zariski closure of the K rational points. Okay? So the main result, which I'll put in quotes because I haven't actually written everything up yet. There are a bunch of steps, and I've written most of them, but not all of them. So let me call it theorem in quotes. So the answer is yes, actually, in a somewhat more general context. So if K is the function field of a curve over a perfect field. Okay, so this question is about curves over finite fields. So instead of finite, I say just perfect. Then, okay, and G is connected, doesn't have to be connected, linear algebraic group, oh sorry, it does have to be connected. Connected linear algebraic group over K with g of k dense in G, then G is unirational. Okay. So let's see, how much time do I have left? I have till 12 minutes, so I have half an hour. So let me discuss, at least in some detail, the various steps of the proof. Okay. So broadly speaking, it breaks up into two steps. Step one is show that g of k dense implies pick of gks. So ks is a separable closure of k is finite. And step two is show that if gks is finite, then G is unirational. I should say, by the way, step one is valid over any field finitely, the function field of any variety over a perfect field. Okay, so this second step uses the fact that it's a curve, the function field of a curve. This first step doesn't. Okay, so let me discuss this. So first of all, using sort of this open cell stuff plus, okay, some not entirely trivial arguments, but you can reduce to the case that G equals U is wound unipotent. Okay, so I'll assume that for the rest of the talk. Okay, so now I want to go from the density of the rational points to the finiteness of the separable Picard group. Okay, so let's assume U of k is dense. How do I say anything about the Picard group? Yeah, so Ketz a few years ago introduced this, what he called the restricted Picard functor. So what is this? Let's suppose X is some sort of K scheme. We'll be interested in the case when X is one of these wound unipotent groups, but let's say X is a K scheme. Then you can consider, by analogy with the sort of more classical Picard functor, you consider this functor in the category of smooth K schemes to abelian groups. She denoted pic plus X over K. So what is this? So I should say the difference, this is the plus just comes from the fact you're restricting, instead of all K schemes, you're only looking at the smooth ones, okay? So you take T goes to pic of X times T modulo the pullback of pic T. So this is by analogy with the usual Picard functor. Now this isn't quite the right object. So if you're familiar with the sort of classical Picard functor, there's this annoying thing you have to do for technical reasons, which is you have to sheafify. So I won't worry too much about that, particularly because in our context it won't matter. But strictly speaking, pic plus is the étale sheafification of this naive Picard functor. In our case, this actually doesn't matter, but in general, you have to do this. So the reason it doesn't matter in our case basically is because we're interested in when X is one of these wound unipotent groups. And in that case, first of all, X is a rational point. And second, the only units on X are the constants. So basically, for these two reasons, it doesn't matter, this sheafification. But at any rate, we consider this functor, okay? And so now here's a theorem of Ket. If X is a form of some affine n space, X over K, so over K bar it becomes affine n space, then, X admits a regular compactification then this thing is represented by a smooth unipotent K group containing no non-trivial unirational subgroup. Okay. So this is nice. You sort of have either, I mean, the novelty of this is that X is not proper, right? So for the classical Picard functor, the representability results are for proper varieties. This is a non-proper variety, it's affine. But he proves under this assumption that there's a regular compactification that this restricted Picard functor is represented. Okay? Once you get that it's representable by a scheme, the fact that it's unipotent and has no non-trivial unirational subgroup is sort of easy. But okay, so the real result is the representability. Unfortunately, there's this fly in the ointment here, regular compactification. So, of course, it's a big open problem whether these things have a regular compactification. So, I'm working on proving, I think I know how at this point. In fact, I'm working on a more general result than just these forms of the affine line, but let me just black box, without discussing the details, that this, okay, it's in progress, holds without the assumption of the existence of a regular compactification. Okay, fine. So now once you have this, this is a group, so if you take the identity component to this thing, it's a unipotent group scheme, it's a smooth unipotent group scheme, smooth connected, that has no non-trivial unirational subgroup. And so if this result is to be true, then in particular, it had better be the case that pic plus x over k has only finitely many rational points. And of course, this is just pic x. So, sorry, u. Called it U before? Okay, so it better be the case that this is finite. Okay? And so it's not very surprising that proving this finiteness is an important step in the proof of this general result. Okay? So the first step now will be to show, in step one of step one, will be to show that pic U is finite. And this is a consequence of a more general result. So if X is a smooth, okay, let me phrase it this way. K is a finitely generated extension field of F, which is algebraically closed. X, a smooth K scheme, a finite type. Then, for any positive integer n, the quotient of pic x by n times pic x should be finite. Maybe you can't see that. Is finite. Okay. Okay, so the proof sketch, let me just give the sketch. So you can write x, or you can spread x out so that x is the generic fiber. Well, let me put it this way. So k you can write as the function field of some variety v over f. And then you can spread x out to a smooth v scheme. You may have to shrink v, I don't care about that, maybe after shrinking v, to a smooth v scheme script x. Okay? So in other words, x is the generic fiber of this script x, and script x is, oh, I should say v is smooth over f. And now, because of the smoothness, and in particular the regularity of script x, the map from the Picard group of script x to the Picard group of the generic fiber is a surjection. This is by regularity. And so basically you reduce from proving this for x over k to script x over f. Okay, so you immediately reduce to the case when k equals f. Okay? And then when k equals f, okay, let's pretend, so now k is f. Pretend x is proper. When it's not proper, you have to do something. Let's just pretend it's proper. When it's proper, then you can consider the Picard functor. Pick x over k, or x over f, sorry. And that's going to be an abelian variety because of the smoothness. And now it's just the fact that for an abelian variety A, right, A of f, it's going to be an extension of its Néron-Severi group by an abelian variety. Néron-Severi is finitely generated. That's not going to present an issue. When you take it mod n times it, that's finite. And if you have an abelian variety over an algebraically closed field, then this quotient is also, in fact, it's 0. Okay? So that's basically the idea. All right. So now, when we apply this in our context, with x equals u, the point is that it's not hard to show that pick u is p to the n torsion for some n. And then you get that pick u is pick u mod p to the n pick u. Okay, so remember k is a finitely generated extension of this f, which is perfect. It's not hard to reduce for the purpose of proving this finiteness to the case when f is algebraically closed from the perfect case. And then when f is algebraically closed, this proposition tells you that this is finite. Okay. So that gives you the finiteness of pick u, and in particular, it tells you that or equivalently, it tells you that this has finitely many rational points. Okay? Fine. So now, suppose that I have a wound unipotent group U with U of k dense. I want to show that pick of U ks, so I want, this is finite. Well, this is equivalent to saying that the restricted Picard scheme of this thing is a tal, dimension 0. Okay. In other words, I want to show that there is no non-trivial map from a unipotent group, let's say of dimension greater than 0. Well, actually, it doesn't matter. There's no non-trivial map from a unipotent group V to pick plus u over k. So there's not exist, say, non-constant such map. So what is such a map? Such a map is the same thing just by the definition of the restricted Picard functor. It's an element of pick u times v, modulo pick v. Let me just wave my hands and not worry about this quotient here. Okay, but if I have an element of pick u times v, that's the same thing as a map from u. So now I sort of switch the roles of v and u, and it's the same as a map from u to pick plus v over k. And now, what's the point? The point is that this is finitely many rational points. That's what we just proved. Okay? And this has dense set of rational points. So this dense collection of rational points has to go to one of a finite list of points. That means that all of u has to map to one point. Okay? So this is constant, which tells you this line bundle is really in sort of this direct sum, and that actually implies that this map also is constant. Okay? All right, so that's step one. So, by the way, I didn't assume here anything about k being a function field of a curve. This works for the function field of any variety over a perfect field, everything I've done so far. Okay, it's in step two that I need to assume it's the function field of a curve.
So you have this attached implication.
Sorry, what?
So you talk about pick
Yes.
x, but you have the rational points of pick plus. It's not clear a priori that the map from pick x to pick x plus of x of k is onto.
Yeah. So this is actually kind of relates to this issue I mentioned before of whether you have to sheafify. So in this case, you don't have to I don't want to worry about this too much, but in this case, you don't have to sheafify because x in this case, it's a unipotent group, so it admits a rational point and no non-constant units. And that implies, for the same reason as with the classical Picard functor, that implies you don't have to sheafify. Yeah. Okay. So, step two is I want to show that if pick UKS is finite, then I want to show that U is unirational. Okay, so first of all, why is this a reasonable thing to hope for, maybe? So there's a theorem of Oesterlé from, I don't actually know when it's from. You'll have to ask Ofer. But if G is a unirational group over some field K, then the Picard group, the separable Picard group, is finite. Okay? And so then it's natural, given this theorem, to wonder if you can go in the reverse direction, or at least when you can go in the reverse direction. So when K has degree of imperfection greater than 1, which this just means that the degree of this extension is greater than P, the converse fails. So there are examples of Totaro over fields of degree of imperfection greater than 1 of unipotent groups, wound unipotent groups that have trivial Picard group, but you can show they're not unirational. Okay? So the converse fails when the degree of imperfection is greater than 1, but so the hope then is to prove, so this is the result, converse is true if the degree of imperfection is just 1. So in other words, if this is an extension of degree 1. So this is where I need the curve assumption. That's a function of a curve as opposed to a higher dimensional variety. Okay. So how to... Oh, sorry. Yes. P. The converse is also true if it's 1, but that's not very interesting. Okay. So how to show this? Well, let me discuss the first step, which can be done. So this is what, step 1 of step 2 or something? It can be done in at least 2 different ways. Let me discuss one of them. Here's the important proposition for the first approach. So suppose that U is a wound unipotent group described by an equation as earlier. So, okay, what is this thing? So I have F. This is a polynomial in n variables, and it's a so-called P polynomial. So what this means is that it's a sum of terms of the form Cij, xi to the p to the j. So each term is just some constant times one of the variables to a power of p. And that's exactly what you need to ensure that this is actually a subgroup. Okay? You need one of these additive polynomials. So this is called a p polynomial. And I further assume, which you can always arrange when your group is wound, this is not really a restriction, it's just I need it for this to be correct. Assume that the so-called principal part of F say what that is in a second, has no non-trivial zeros over K. So what is the principal part? So if I write down, so for instance, I had this example from earlier, right, of this unipotent group given by the vanishing of this polynomial, this p polynomial. The principal part is you just take the leading part in each variable. Okay, so it's y to the p minus ax to the p. That's the principal part of this thing. In general, you just take the leading term in each variable. And we assume that if you add those, there's no non-trivial zero. So in this case, that's true, right? Y to the p minus ax to the p is 0 with x and y and k, then x and y both have to be 0. Okay, that was in fact the key to that earlier proof that U was wound. Okay? Right. So assume the principal part is no non-trivial zeros. And let's write out the principal part. So the principal part of F, P equals the principal part. Let's say that this equals the sum I is 1 to n of Ci xi to the p to the ni, and let n, big N, be the max of the ni's. So it's just the max, it's the degree of f, okay? Then you can consider, instead of the full restricted Picard functor of u, you can consider the part, so u acts on itself by translation, and therefore acts on its Picard group by translation, and in fact you can promote this to an action on the restricted Picard functor. And so you take the u invariance, and you take the maximal smooth subgroup of this, so let me just say smooth. So the points of this correspond to translation invariant line bundles on u. So this has dimension equal, so you can explicitly compute it, it's p to the n minus the sum over all I of p to the big N minus n. Okay. In particular, if pick of u ks, or let's say if pick plus u over k is finite, if it's étal, so I'm operating under that assumption, then you deduce that p to the n is the sum of p to the n minus ni, or equivalently you can cancel, right? 1 is the sum of p to the negative ni. And this, in turn, is equivalent to saying that this principal part of f, right? So you can regard this principal part as a homomorphism from kn to k. And this equality here, because we're in degree of imperfection 1, this equality is equivalent to saying that this map is surjective. In other words, p is a universal polynomial for k. Okay? Now, groups defined by polynomials with universal principal part are examples of a type of group that I introduced recently called asymptotically universal unipotent groups. So these are examples. So this implies U is asymptotically universal. So actually, what is the definition of asymptotically universal? So you can give a sort of more intrinsic definition without referring to any equations. So here's the definition. A smooth unipotent group over K, U, is called asymptotically universal when the following condition holds. Okay. For any right exact sequence of K-group schemes, finite type K-group schemes, U goes to E goes to GA. So this is the additive group. So you have a right exact sequence. U maps to some finite type group scheme E, and there's a quotient is GA. Then E contains a copy of GA. Okay. That's a slightly weird definition. It basically says that if you form quotients of wound groups by quotients of U, then the result is still wound. That's basically what it says. Okay, so in general, a wound group modulo a subgroup is not wound, but these are groups which do have that property, and furthermore, all of their quotients have that property. Okay? So this is asymptotically universal, and this equality, in fact, exactly says that this U is asymptotically universal. Fine. I should say also that I'm only considering certain types of U here. These are the U that are commutative in P torsion, but it suffices to consider those. I won't get into why, but it suffices. Okay, so now these groups are useful for two reasons, but let me just mention one of them, which I need for this unirationality. This is actually, it's probably not clear from anything I presented, but this is by far the hardest part of the whole talk, actually, proving this result. So you can make this definition. This definition is over any field, and this theorem is also over any field. Well, I say any field that's mentioned in the theorem. So if K is a separably closed field, then, and it may as well be a finite degree of imperfection, but it doesn't matter actually, then, let me say imperfect maybe, just to be perfectly careful, imperfect separately closed field, then any asymptotically universal group, the asymptotically universal groups have a very rigid structure. The universal unipotent group U over K admits a filtration I guess UN is bad notation because I used it to note the unipotent groups earlier. Maybe I should do something like this. Okay, so it admits a filtration such that for all I, between whatever and whatever, VI mod VI minus 1 is isomorphic to one of two groups. Let me just say to one of two groups. It doesn't matter so much for me what the groups actually are for the purposes of this talk. But the point here is split groups are simple because they admit a filtration by GA. All the quotients are GA. So what I'm saying here is that asymptotically universal groups are sort of almost as simple. They admit filtrations where all the quotients are one of these two groups. So you need two instead of one, but whatever. And there's another wrinkle, which is one of these two groups is actually not smooth, but it's not such a big deal. In fact, it's actually a good thing for many purposes. Yeah?
So is it if and only if? I mean,
It is if and only if, yeah. If for a smooth group, yeah. For smooth unipotent groups, it's if and only.
But if it admits filtration like that,
Yes.
whatever are those groups,
Then it's asymptotically universal.
you will tell us something.
What?
What are the groups?
What are the, okay, fine. You want to know what the groups are. I wasn't going to say, but okay. Okay, before I say what they are, let me just say, I'll say one sentence here about how this, you get from here to unirationality, which is all these groups, in fact, using this, you can prove all these groups are unirational. All the asymptotically universal ones, and therefore this U you started with was unirational. You can imagine that somehow you can use this rigidity to prove this. Okay, so now your question, what are the two groups? Okay, so the two groups, since I have 3 minutes, I may as well say. So one of them is just, you take the Weil restriction of alpha p from k to the 1 over p down to k. So this is totally non-smooth, but it's whatever. It's a group, okay. So this is one of them. The second group, it's a bit more complicated to describe. So when k has degree of imperfection 1, it has a simple description. It's just this group I mentioned earlier, this counterexample to Oesterlé's result when you weaken the inequality, it's this quotient. In general, what do you have to do? You have to take so let P be universal homogeneous, just pick your favorite one, universal homogeneous degree P polynomial. It's not hard to construct such things. Basically, you choose a basis for k to the 1 over p over k and raise everything to the p. And then let L be homogeneous non-zero degree 1, so linear. Okay. And then you can just take your U, this second group is going to be the group P plus L equals 0 inside GA to the whatever power it is. I guess it's P to the R, I think, where R is the degree of imperfection. Okay. It turns out that it doesn't depend on choice of P and L. You get the same, because of this separably closed assumption, they're all the same group. So this is the second group. Okay, so at any rate, this is actually the hardest part. Let me just mention one last theorem since I have a minute left. So these asymptotically universal groups, which are important for solving this problem, are actually very useful for other problems. And the reason is First of all, they have this rigidity, which allows you to study them more easily than an arbitrary unipotent group. And then the other property they have is that they're sort of, they're ubiquitous. There are a lot of them. By which I mean that if U is a smooth, connected, or let's just say wound p torsion, commutative group, then there is an inclusion of U into some W with some co-kernel like this, where W is asymptotically universal and wound. Oh, I lied here, God. Wound. Okay, so if this is asymptotically universal and wound, so in particular it has this rigidity, it has this filtration, and V is a vector group. So any U that's, so you can always sort of filter unipotent groups by things like this, commutative p torsion, and any such thing can be stuffed inside a wound asymptotically universal thing, so it has this nice filtration with the co-kernel even being a vector group. So this means for the purposes of many questions about wound unipotent groups, you can reduce to the case of these asymptotically universal groups, which you can then study using this filtration. Okay, and I'm 1 minute over, so I'll stop.